Okay, very good. I'm happy to welcome you all to the AI seminar today. Where our speaker is Yi Wan. He's a graduate student, a PhD student in the department. I've been a supervisor for several years now, I think 3 or 4 years, and he comes to us from University of Michigan, where he studied with Ben Kuipers. And he's done a lot of interesting work. He's done work on average reward with new average reward algorithms with Abhishek Naik, and with he's done work on carrying the options framework to the average reward case with Shangtong Zhang. And most recently, he's been working as an intern with Microsoft, with Harm Van Zyne. It was last summer, and I think it's worked so well that they've kind of kept him working on that project. And that's what he's going to talk about today, which is sort of the key ideas in theory in model-based reinforcement learning. And so probably he's fairly far along, and I expect him to finish sometime this year. I think he's doing really well, and I hope you all will welcome him to give his talk today. Yuan.
Thanks, Rich. Thanks for your introduction. And okay, so let me share my screen. So can you guys see my screen? Cool, nice. So today I would like to share with you guys this work that I did during my internship last year in Mila, and this is a joint project between Mila and Microsoft. I have met so many great people there, I mean virtually, but it's still a lot of fun. And today, I think maybe some of you guys have also joined this talk. Ali or Jenna or Ida, Saras, Harm, anyone who joined, you want to say hi to other people?
Hi everyone, I'm Jenna Janathanan. I'm a postdoc at PlaNet working with Sarath and Dyna. Nice to meet you all. And I did my PhD with Satinder.
Yeah, thanks, Jenna. So Ali, are you here?
Yeah, me too. Hi everyone. I'm Ali. I'm a master's student working with Sarath in Mila. Nice to be here.
Yeah, thank you guys. Thanks for joining us from Mila. Yeah, so this work is mainly about evaluating a property of model-based reinforcement learning. And I started to think about this problem when I started the internship, and I kind of learned what they are doing, what Mila and Microsoft are working on. And they're thinking about evaluating the progress of model-based reinforcement learning, because we have seen a lot of great progress in reinforcement learning in recent years, and especially model-based reinforcement learning. For example, AlphaGo is an example, a very good example of model-based reinforcement learning. And MuZero, maybe some of you guys know, that is also a good example of model-based reinforcement learning. In MuZero, they try to solve Atari games, the video games, by using some model-based reinforcement learning algorithm. So I just learned that they're working on trying to come up with some way to evaluate those algorithms. And I found it pretty cool. So I just decided to keep working on that line of research. And that brings me to some results. And those results are what I want to share with you today. So let me get started. So first, let me just briefly introduce what I mean by reinforcement learning. So in reinforcement learning, you have an agent and then you have an environment. And these two elements, they interact with each other. So first, your environment sends a state, the environment state, and the reward to the agent. The agent observes the state and the reward and then takes an action. And the action is received by the environment, and the environment sends the next state, the state at next time step, and the reward at next time step. So there are some elements inside of the agent. The first element is the agent's policy. And a policy is basically a function that maps from a state to an action. So you might think that your agent is always interacting with the environment and it needs to choose some action given some state, and that function is the policy. The agent also has a value estimation, which the value is basically the estimated total reward in the future, given some policy that agent wants to learn. And the agent may also maintain a model, and the model is basically some prediction about the future next state and next reward given the current state and current action. So basically it's a simulator of the real environment. So if the agent has a model, then it can use the model to generate some simulations for planning. So by planning, I mean using the model to improve your policy or your value function. And finally, the agent can also just directly improve the value function or the policy using the real data, not by the simulated data. And that's what we call learning. Okay, so this is like a very short introduction about reinforcement learning. And next, we're trying to think about this problem. How would we evaluate a model-based reinforcement learning algorithm? So in order to answer this question, maybe the first question to answer is, why would we learn a model? Why is it not enough to just do model-free learning? Why is it not enough to directly improve your policy or value function using the real experience? Well, a lot of people say that it's because learning a model and planning with the model give you a much better sample efficiency. And by sample efficiency, I mean you can achieve some level of performance using less samples. So if you can achieve that goal, then you can say your algorithm is more sample efficient. But is that really true? I'm just wondering about this. Well, in some cases, I think that is actually true. When learning a model is very easy, or you're just given the model, you don't really have to spend too much data. I mean, you don't need to collect too much data from the real environment. But if the real environment is very complicated, then learning a model is not necessarily easier than directly learning a policy. So overall, I think the conclusion is that it's unclear whether or not learning a model is more sample efficient than learning a policy directly. Some other people say that, well, learning a model is good because your algorithm with a model can adapt to the changes in the environment. So in this talk, I'm going to focus on this point. I'm going to show that we can actually construct a way to evaluate model-based algorithms to actually evaluate their adaptation to the changes in the environment. To see why this is true, we can just look at this simple example. So here you have a small grid world. This small grid world, so you have two boundaries here. So you cannot move to those black cells, but these like white cells, they're empty. So you can just move from one to the other one. So these green cells, they actually mark reward of 4. So this is actually like a higher reward terminal state. And this state is like a lower rewarding terminal state. So in this domain, you really want to move to the left because this gives you higher reward. And here I use the arrows to draw the policy that agent wants to take. It wants to move to the left. And when the environment changes, so now I just changed the environment so that this terminal state has less reward. So right now the reward is even less than the reward here. So now the policy should be that moving to this other side of the corridor. So you see that, well, when there's a change in the environment, the policy can change abruptly and can change globally. But the model only changes very little because you just need to change the model here, saying that, well, going to here, your reward is no longer that high reward, but now it's a low reward. Okay, so by that kind of change that I just mentioned is what we call, actually what they call, because I just learned this from Mila in Microsoft. They call it a local change. So when there's a local change, change the model to incorporate that change, that local change in the environment, does not need too much real data because you just change the environment a little bit. And planning, as I said, it doesn't need any real data. You can just generate some simulations from the model and then improve your policy. So this looks very good because you don't really need too much data when the environment changes locally. But if you think about model-free reinforcement learning, well, if there's a local change, then as you just saw, there could be some global change in good values or policies. And you really need to collect much more real data to update value and policy. So in this case, let's this small region is the model change region. So your model needs to be changed inside of this region. Which value or policy, for all these states here, their values, their policies needs to be changed. And that's why model-based reinforcement learning could be more sample efficient if we have a local change in the environment. So that's basically the underlying motivation of that evaluation methodology that we want to introduce today. Okay, so here's the outline of the talk. So first, I will formally introduce you this evaluation methodology called LoCA. And next, I will show like how using LoCA, the 5 failure modes of modern model-based reinforcement learning algorithms that we have identified. And finally, I'm going to present you with one algorithm that is adaptive and doesn't have this any of these 5 failure modes. And this algorithm is what we call modified linear Dyna. Okay, so let's start the first point. So when we talk about adaptation, there are several things that we want to talk about. First thing is that when there's a change in the environment, you really have to discover that change. Because if you don't find a change, you would never know that, well, there is such a change there, and there might be some better policy. The second thing is that you want to learn a change. You want to incorporate that change into your model so that you can do planning using that model. And that's the third point. So typically, exploration is a very difficult problem in reinforcement learning, and especially in modern deep reinforcement learning algorithms. By deep reinforcement learning, I mean reinforcement learning using neural networks. So for these algorithms, it's very difficult to do exploration. And so Locus idea says that, well, is there any way that we can design our evaluation methodology so that the algorithm does not need to have a strong ability, exploration ability. So we just want to evaluate the second 2 points, but not the first point. And that is what LoCA proposed to do. It only evaluates the second and third point. And how does it do that? Well, the idea is also very simple. So let's go back to revisit this small grid world. So we actually have changed this part. So that's the part that we want the model to be adjusted for. So really the idea is just adding a bar here. And this is like a one-way passage in your environment. So by one-way passage, I mean, you can move to this direction, but you cannot move to this direction. You can move to the right if you're within this small region that consists of 3 cells. And that means if I just initialize the agent inside of this region, then the agent cannot get out of this region. And then what I want to do is that after the environment has changed, I would just place the agent inside of this region and let the agent observe that there is a reward change in the environment. So that's pretty easy, because now the agent doesn't have to really try to explore over the entire state space in order to find this change. Okay, so that's the idea. Okay, so that brings us to LoCA. And I think I have already know the motivation and the basic idea about LoCA, so this should be very easy for you to understand. So first, LoCA has 3 different phases. It's like experiment has 3 different phases. And also in each phase, we have a training and we also have evaluation. So training just means that you get some real data and you try to improve your policy, try to improve your value function. And evaluation just means that you don't change any of your parameters and you just try to follow the policy in the environment and see how much reward you can collect during your like 1 episode. So here, this is what you have in the first phase. In the first phase, this is higher reward. This end has higher reward. This end lower reward. And I use blue color to denote that you can actually, it's actually the initiation, sorry, the initial state can cover the entire state space. So really, I mean, you can just initialize your agent anywhere in the state space. And for evaluation, we would only initialize the agent in between these 2 terminal states, and we will actually count the number of steps for the agent to reaching to the correct terminal state. And then if that number of steps is like lower than some threshold number of steps, then we say, well, this episode is successful, and otherwise we say that it's not successful. So overall, we want to evaluate how many successful episodes, the fractions of successful episodes. And that's the idea of evaluation. So this is the first phase, very simple. The second phase, you change the reward. And also you just place the agent inside of this small region and you let the agent observe the change of the reward. And for evaluation, it's actually the same. Again, you start the agent from the same initial states and you want the agent to find the right terminal state. So this time, this terminal state has higher reward. So really the agent should be going here. So again, you just count the number of time steps and compare it with some threshold that you set. In third phase, you give the agent full access. I mean, the initial distribution covers the entire state space again. And this time, the evaluation remains the same as the second phase. Okay, so LoCA actually has provided with some specific reward setting. So this green reward just means you have a reward of 4. This yellow cell means you have reward of 2, and this gray cell means that you have reward of 1. But you can definitely set it to some other numbers as long as like this is the highest reward, median reward, and lowest reward. So you have probably seen like 2 potential problems or difficulties when you define some such kind of evaluation. The first thing is that you have to find the threshold time steps. So as I said, you need to compare that threshold with the number of time steps you have actually used in each evaluation episode. But finding this threshold time steps could be not easy, could be tricky. And the second thing is that you really have to find those initial states in between two terminals. And for some problems, this is not easy. So for this problem, this is like an example. This is like a great world problem. it's probably quite straightforward for us to tell what state is in between two terminal states. But in general, in general domains, this is not quite true. So LoCA is actually an abstract evaluation methodology, and I'm just using a grid world as an example to illustrate it here. But in general, you can just apply LoCA to any domain, as long as you can set the terminal states, the reward in that domain, then you can just apply LoCA there. Okay, so so this is the original version of LoCA. This is what I learned from them. And I was just then thinking that, well, maybe I can just simplify this because this looks a little bit complicated. The first thing that I realized is that we don't really need this cert phase, because you actually can, the agent can already learn that there's a change in the environment, and in the evaluation runs, it can already discover the right terminal state, which is this yellow state. So maybe we can just remove phase 3. And also, the other thing that I want to remove is the threshold time steps and also the initial state distribution, because that also looks a little bit artificial. So this time, I just propose to use the discounted total reward instead of using the number of time steps reaching to the terminal. So really here, so this time we can just initialize our agent from anywhere inside of the state space, and we just count the discounted total reward the agent would collect in each episode. So in this domain, no rewards will be received here. There will be only one reward here and one reward here. So by adding a discount factor is like you treat future rewards to be less important than your current reward. By adding a discount factor, you can encourage the agent to get the reward as soon as possible, so that the agent can actually move to the right terminal, like find the shortest path to the right terminal. Okay, that finished the first part of the talk. I hope that's clear to you guys. And now I want to start the second part. So if you have any question, you can ask now or just later if you are confused about the first part. Okay, so maybe, yeah, I can start the second part. Okay, now I just want to introduce 5 different failure modes that we have identified in modern model-based reinforcement learning algorithms using the LoCA methodology. First, let me present these 2 simple failure modes that should be simple, very easy. The first failure mode is what we call the lack of state coverage. This basically says that, well, if your updates to your value function to your policy does not cover the entire state space, that can be a problem, because really you want every state to be correct, to have the right action, the right action to take for each state. And second failure mode is what we call the policy dependent model. And this failure mode is a little bit more tricky, but basically the idea is that you don't want your model to depend on the policy that you use to learn the model. You want your model to predict things well. You want your model to predict the correct thing, but I will just explain what it is afterwards. So for each of these 2 failure modes, we have designed a corresponding algorithm. So as you see that we have 3 algorithms, and this first algorithm is a baseline algorithm. It's a very good algorithm, and everyone knows that it is good. And the second and third algorithm, they're the algorithms that we designed that are flawed, and we want to and these 2 algorithms have the corresponding failure modes. They actually falls in corresponding failure modes. So both the first and second algorithm use this update rule to update its value function. And the third algorithm use this update rule to update this value function. So for those of you guys who are familiar with reinforcement learning, you probably have already found that this is just a value iteration algorithm. So basically, the algorithm is that the agent is exploring an environment and learning the model, and then apply value iteration to update some state. And the first algorithm says that, well, you should just randomly pick a state to update, randomly pick a state from the entire state space to update. Second algorithm says that, no, you should just update your current state. The agent's currently, the state that the agent is currently visiting. And this third algorithm is a little bit more tricky. It says that, well, I don't want to predict what will happen in the next time step. Instead, I want to predict what will happen in 2 time steps. So the first time step, what will happen in the next time step depends on my state, my current state, and the action that I want to take. But the state after that, the state in 2 time steps, it depends on, well, the behavior policy, the policy that you use to collect the data. So it's like given a state, given an action, and given your policy, the policy that you would use to choose the action for the next state, what would be the resulting state in 2 time steps? And what would be the cumulative reward in these 2 time steps? So these are the meaning of this R hat 2 and P hat 2. Okay, so we're gonna just explain what would happen if we just run these algorithms in the grid world domain that I just showed you. So for this first algorithm, again, this is a very good algorithm, so we should just expect that it works well. So in this domain, first you want to move to the left hand side. And here I use orange color to denote that this update is actually applied to over all the states over the entire state space. And that's why you can actually get the right policy for each state. And by the way, the policy is derived by taking a greedy, by taking the argmax over this inner part. Kind of a little bit technical, so if you're not familiar with value iteration, that's fine. But just intuitively, your policy would be good because you can update for each state here. In the second phase, again, because you're just randomly sample a state to update, so still you're updating for all the states in the environment in the grid world. So again, you would get the right policy. So this is the right policy. Now let's talk about the 2 flawed algorithms. This first flawed algorithm still works well in the first phase, and that's because the agent can really observe all the state space. Because in the first phase, remember that agent is initialized over the entire state space, so it can get every state observed, and that's why in planning also updates for all states. But the second phase is problematic because the agent only gonna observe those states. And if it only observes those states, the policy and value for these states will not be updated. And that's why they're still saying that you should move into the left because they're not updated. So that's the problem. That's what we call the lack of state coverage problem. Okay, so this is for the third algorithm. The third algorithm, if you learn a model, a 2-step model, starting from a state and taking an action, you would move to this state. And then because your behavior policy says that, well, moving to this direction is actually better. So you should also expect that the state in the next 2 steps will be a state here. However, if you just try to think about what would happen if I choose an action that moves to this direction, because the behavior policy says that you should move to this direction. So the model predicts that starting from this state, taking an action, you would actually ending up with the same state as you started from. And that actually is problematic. You don't see that it's problematic in the first phase because, well, comparing these 2 cases, you see that, well, this is better because you're moving to the right terminal, you're getting closer to the right terminal. So this action should be better. And that's the right action to take in the first phase. But now if we just move to the second phase, this becomes problematic because you're gonna say that, well, again, because your model never updates, that means your model still remains the same as this. But then you will try to move to this part because you can't really find that this, because like if you start from here, you will never be able to get here. Your model will never be able to tell you that you should get there because the model says you will stay in the same state. And that's a problem. So all the policy will remains the same. I mean, remains the same as what you get in the first phase, except for these states, because for these states, the model actually tells you that, well, you will reach a terminal state with reward of 2. And that's why you should move to that state. So these are the only states that you can get the right action to take. Okay, so hopefully I just explained things well. And this is what we call the policy dependent model. It shows that if your model, the target of the model depends on the policy, that can be a problem if your environment changes. If your environment does not change, that may not be a problem. But if the environment changes, that can be a problem. And then we just run an experiment to illustrate this point. So basically, you have 3 phases here. And this is the LoCA experiment, as I said. And these 3 algorithms, the orange, green, red color, they correspond to the 3 algorithms that I mentioned. This is a good algorithm. These 2 are the bad algorithms. And in addition to these 3 algorithms, I also show an optimal policy, what would an optimal agent perform, how much return it will get, how much cumulative reward it will get. And also how will a model-free algorithm perform. So we were all talking about a model-based algorithm, and this source lambda is a very good model-free algorithm in the tabular setting. How will this algorithm perform? We just want to compare, make some comparison. And from the graph, you can see that, well, first this perfect algorithm, it works really well in the second phase, because you can see that it can actually, after some time, you can actually find the right terminal to move to. But both these 2 algorithms, the red one and green one, they're pretty good in first phase, but in the second phase, they didn't do well for the reason that I just explained. And star-side algorithm, because it's a model-free algorithm, does not learn a model. It needs to relearn all the things when the environment has been changed. And that's why this algorithm is not doing well in the second phase. But in the third phase, given that the agent has access to the full state space, all the algorithms end up being pretty good after training for some time. So you might want to ask, what if you have function approximation? Because we just mentioned that, so this is really a tabular setting. What if you have function approximation? So by function approximation, I mean, you have a really large state space, so you don't really store for each state a value, or store for each state its model, what would happen in the next time step. So when you have function approximation, for each state, you will assign a feature vector, which is a real vector to represent that state. So a feature can be shared by multiple states. So in that way, you can reduce the complexity, I mean, the memory that you use to store the value function, the model, etc. So when you have function approximation, the problem is that you can't really cover the entire state space because the state space can be just too large. And in that case, we don't make the strong argument, but you can think that this idea applies similarly. You still need to have a good coverage over the feature vector space. Although maybe you may not be able to cover the entire space, but you may not be able to visit every particular possible feature vector. But you really want that, well, the feature vectors that you use to update can have a good coverage over the space. And for the second point, a policy-dependent model, well, when you have function approximation, your model is always depends on the policy, and that is because, well, when you use function approximation, your model has limited capacity, and it will always be influenced by the data that you collect. And the data that you collect is influenced by the behavior policy. So this is kind of complicated, but intuitively that also makes sense. Let's say your behavior policy only collects some data for some part of the state space, but really you would not try to visit that part of the state space when the environment has been changed, because that's pretty like not quite useful. You just want to visit some other parts of the state space. And your model can be just incorrect or not doing well in that other part. So overall, I think these two failure modes apply still to the function approximation case, but we just need some softer statement for the two failure modes. Okay, so now let me introduce the third failure mode, which is what we call action sequence condition model. And what I mean by saying this, well, so here just to draw a small diagram, and this solid curve, it stands for the behavior policy, a trajectory visited by the behavior policy. And the action sequence condition model just says that given the current state and an action sequence, so this is an action sequence, like 5-step action sequence. So this kind of model is different from the one-step model because it's saying that what would happen if you fit with the model in an action sequence. So in this case, this can be a problem potentially because the behavior policy would only visit a small set of the possible action sequence. However, in the new environments, in the environment that after the change of the environment, your behavior policy may not be good anymore, and you might want to discover some better behavior policy. But that behavioral policy, you haven't learned a model that predicts what would happen if you follow an action sequence according to that behavioral policy. So really all these dashed lines, dashed curves, the model cannot make accurate predictions on these trajectories. And that can be a problem. So one example that I want to give you is this algorithm called MuZero. Remember that it's one of the state-of-the-art model-based algorithm. So this algorithm uses this kind of technique. In fact, uses what we call the Monte Carlo tree search algorithm. So the algorithm says, starting from the state, you want to ask, what if I take some particular action sequence? What would happen in the future? So that actually can be problematic, just as what I said here, because when your environment changes, you want to consider other action sequences, but your model is not trained for those action sequences well. And also you can see that when the length of the action sequence is pretty long, the complexity of the model grows exponentially. So really you're just making it too difficult for the model to learn things if you use a large action sequence. Yeah, and by the way, this is what we call Monte Carlo tree search algorithm. So the LoCA paper that the Mila and Microsoft people wrote actually demonstrated that this algorithm cannot perform well in phase 3. Remember that previously they have 3 phases and they evaluate performance in the 3rd phase. So this curve corresponds to the MuZero algorithm, and you can see that although in the 3rd phase, a model-based algorithm should be able to perform pretty well, because even in the 2nd phase, it should be able to perform well. But really, it's just starting from a very low part. So this curve corresponds to the 3rd phase MuZero performance. That's a little bit unfortunate. So that's basically about failure mode 3 and an example that falls in this failure mode. And now let me introduce the final 2 failure modes. I think these are the most interesting failure modes. The 4th failure mode says that if you learn from outdated data, then that can be a problem. By outdated data, I mean the data that from the old environment, the data before the environment has been changed. And 5th failure mode is what we call the catastrophic forgetting. And that's basically a problem when you learn with a neural network. And I'll explain it a little bit later. So now I try to draw the data. So this is the two phases, and I use different colors to represent different phases. And these are, you can just abstractly, you can just think these are the data that you collect in different two phases. So if you learn from outdated data, so a very common way to learn from, to do reinforcement learning is to use a replay buffer. So by using a replay buffer, you're just storing the data that you have collected before, and you try to replay the data. You try to learn from the old data that you have collected. So this is kind of a way that's quite similar to supervised learning. Supervised learning also maintains some data set. And you can just think this as you maintain some data set that is always growing. So if you use a large replay buffer, then that can be a problem because, well, once you're entering the second phase, you're still learning from the data from the first phase, and that is not consistent with the data in the second phase, and that can be problematic. And if you use a small buffer, that can cause the problem, what we call the catastrophic forgetting. And basically, the idea is that once you have tried to learn things here, you completely forget the things that you have learned before. So once you try to learn, well, the new phase, what's the right reward model, right policy in the second phase, you just forget things you have learned here. And that is problematic because really you don't want your model to forget because you want to plan with the model. Okay, so we use two modern algorithms to illustrate these 2 points. And in particular, we use this, what we call the richer LoCA domain to illustrate this point. And here you have this is a small robot, and this small robot, this is the first terminal with higher reward, and this is the terminal with lower reward. But then you just change this higher reward terminal to one with lower reward. And this is the small region, one-way passage small region. Okay, so the first thing that you will see is that if you just make plots, so these are the plots that I made we make for the reward model of one algorithm called DreamerV2. So it's basically one modern, very popular algorithm. So and correspondingly, I'm drawing these diagrams, these graphs for illustration. So this is the first phase performance, and you can see that in the first phase, the algorithm is doing pretty well. It's making correct prediction for both two terminal states. In the second phase, well, this corresponds to the case when the replay buffer is very large, contains all the data. And that's why you can see this black box covers all the data that you have collected before. And this is the third phase. So the problem is that once you use the wrong data to update your model, then this becomes not accurate. Remember that this should be even lower than this one after you change the environment, but really this is higher in the experiment. In third phase, well, it's getting a little bit better, but still because you have wrong data, these two terminal states still looks a little bit, it just still looks like the same, but really this one should be lower. Now, what if you can clear the replay buffer? I know the algorithm cannot really do that because it doesn't know the environment has been changed, but well, what if you just have this ability like to clear the replay buffer? That would be the perfect case because you don't have any outdated data in your replay buffer. That's still a problem, and this is what we call the catastrophic problem, forgetting problem. Because as you see, when you try to learn the reward model here, you completely forget what you have learned before. So this should be a rewarding state, but you just forgot it. Although in third phase, it's getting better because you can collect the data over the entire state space. So you can collect the data here to learn reward model here, collect data here to learn reward model here. But in this case, you don't, given that you don't have you don't have data here, you only have data here, your model can completely forget. So that actually corresponds to this diagram. So this is just like a learning curve, which shows that in second phase, the streamer algorithm did not perform well. And in the third phase, if you clear the replay buffer, well, that can be doing well because the reward model is getting right. If you don't clear replay buffer, still the model is incorrect and your performance is also not good. And there's a final comment about this, which is that some people view experience replay as planning. So right now we just mentioned experience replay to learn your model, but we haven't mentioned that using experience, your past experience, to directly update your policy or your value function. Well, that's also a possible way. And some people say that, well, it's actually kind of model because once you store all the data before, the model is basically say, given a state and action, what would be the next state and action? And your past data can actually tell you what would be a next state and action. So some people just argue that, well, this is also planning. But as you see here, this also falls in the same issue here. So once you use, so if you use outdated data for planning for experience replay, that can cause you give some bad value estimates. And if you don't use a large replay buffer for planning, your value estimation could be off in the parts that is not visited before frequently. Okay, so MuZero, as I mentioned before, also uses experience replay, so which means that this algorithm can be problematic when we change the environment. But this algorithm does not only use experience replay, it also uses this like a multi-color tree search algorithm. However, this algorithm needs to use those value estimates. And these values, they're only updated by experience replay. And again, experience replay cannot give you right values. And that's the reason, even if you have this one additional component, it cannot give you the right action to take in the second phase once the environment has been changed. Okay, so I have to be very quick on this third point, which is an adaptive model-based RL algorithm. This is what we call modified linear Dyna. So in this algorithm, basically here I use a diagram to mean what we mean by saying Dyna. And Dyna is actually quite an elegant idea. It says that you should use your real experience to update your policy and value function directly. And at the same time, you make some model and use the model to produce some simulated experience. And most importantly, use the simulated experience to update your policy and model in the same way as what you will do in the direct update. So basically apply the same update, just the data are different, but the updates are the same. So when I say linear Dyna, I just mean the model is parameterized by a linear function approximation. Value function is also linear function approximation. So that's basically the idea about linear Dyna. And you have probably see this part, you have probably noticed this part. So this is what we call a search control. And that's basically the part that gives the model the input of the model, that produces the input of the model, produces what state and action you want the model to generate simulated experience. So in linear Dyna, they used what we call the tabular feature vector, which is basically, some people call it one hot vector because there's only one here and all other elements are 0. So let's see whether or not this algorithm is good for whether or not it falls in any of the 5 failure modes. So actually, first it falls in the first failure mode because of the lack of state coverage. Remember that in function approximation setting, we want the feature vector that we use to plan for to cover the entire feature vector space. But in this case, the feature vector, although the feature vector space is very large, can contain any real vector. This algorithm only plans for the tabular feature vectors, which only contains a small subset of this the feature vector space. And that's why we say that it lacks of coverage. But fortunately, it doesn't have the following two issues. The model that we make is not policy dependent. It's a one-step model, and that's why it doesn't require action sequence. It doesn't learn from outdated data because it does not use a replay buffer, does not learn from the replay buffer. Instead, it directly learns from the current transition, the current sample. And it doesn't have catastrophic forgetting problem because it doesn't use a neural network. And also the feature vector is very sparse. So if you use a linear function approximation and your feature vector is sparse, you don't have the catastrophic forgetting problem. So then the question is, how do we resolve the first issue? And we propose to just slightly change linear Dyna by sampling feature vectors that has been visited before instead of creating these special feature vectors. So in this way, we make sure that if you have visited a lot of feature vectors that covers the entire feature vector space, then sampling those feature vectors and updating for those feature vectors should be good. And this is justified in our experiment. So in this experiment, this blue curve, this is an experiment in the mountain car domain. Again, it's modified to use the LoCA methodology. And this blue curve is our modified linear Dyna algorithm. You see that it adapts pretty well in the second phase. This orange curve is the stars lambda algorithm. Again, the model-free algorithm. Sorry. Oh wait. And this green curve, it's the linear Dyna algorithm with tabular feature vectors. If you just sample tabular feature vectors to plan to update, you see that it's pretty not doing well, even worse than stars lambda in the second phase. And then we just try two different kind of stochasticities in the environment, because remember, this is a deterministic experiment. We just try a low stochasticity and high stochasticity, different versions of the environment. And in both cases, modified linear Dyna can reliably achieve the right terminal in the second phase. And also, when the stochasticity is really high, then it's even better than the model-free learning algorithm, because learning a model can kind of absorb the variance in this, like in the environment. So because the model predicts what would happen in expectation in the next time step. So that can make the algorithm has less variance, and that's why it is doing better here. Okay, so let's wrap up. We have introduced a simple LoCA setup, and we have introduced 5 different failure modes identified using this LoCA setup: lack of state coverage, policy-dependent model, action sequence conditioned model, learning from outdated data, and catastrophic forgetting. And finally, we presented an algorithm that achieves adaptivity in a mountain car LoCA domain. And this algorithm is free of the 5 failure modes that we discovered. Okay, so that's it. Thanks for joining. Yeah, thanks for listening. So any questions?
We have 5 minutes for questions if anybody wants to ask anything.
I'd love to go if you don't mind, Yi.
Hello.
Yeah, thanks. First of all, thanks for the talk. It was very interesting. So one question though is, here you give an algorithm that doesn't have any of these modes of failure. This, I guess, is a 2-part question. Do you think though that if we want to develop like very like strong algorithms, we're going to have to, for like these large domains, do you think we're going to have to like accept that maybe we'll have some of these modes of failure? Or do you think we'll be able to always come up with algorithms like that will be free of all of these and still be able to handle like large state spaces?
So that's a very good question. So I guess your question is, let me just repeat it. So you're asking whether it is possible to design an algorithm that is free of these 5 failure modes and can solve a large domain like Atari games. Is that right?
Yeah.
Yeah. So I think the main challenge, so I don't see a challenge, maybe it's not too difficult to avoid the first 4 failure modes. But the 5th failure mode is very challenging. And you probably know that there are over 30 years of research working on this direction, catastrophic forgetting. And basically, I would say that any algorithm who wants to adapt to environment changes needs to deal with this problem directly instead of using some way like experience replay or some way that uses past data, because really you don't know when the environment changes. And if you store past data and learn from that data, can always be problematic. So in order to get some algorithm, to obtain some algorithm that performs well and doesn't have these 5 failure modes, I think solving catastrophic forgetting is a key challenge.
Thank you.
Yeah.
Does anyone else have any questions?
Hi. Sorry, I have a question.
Sure, go ahead.
For a model not to be policy dependent, does it always have to be one step, or in some cases, for certain environments, can you get away with it predicting over a number of time steps?
So if you want to predict what would happen in the future for a number of time steps, there are basically two strategies. First is that feed a sequence of actions, and you ask, and yeah, I think there are 3 strategies. First is you only predict what will happen if you follow some particular policy. Second strategy, feed a sequence of actions. And third strategy is to roll out your model. You make some one-step model and then you roll out it. You just ask the model to predict the next state and then use the next state as the input of the model to produce the state after that. So these are 3 different strategies, I think. So I think they like each of them has some advantages and disadvantages. First, the strategy, policy-dependent model, as we just said, it's not quite useful when the environment has been changed because, well, the policy remains to be important in the new environment. Second approach, action sequence condition model, it makes the model too complicated to learn, and you may not have like explored well to collect enough data to learn it, to train it. And third model, the one-step model, but you roll out it, there's a problem called compounding error, because every time when you iterate your model, there's some additional error, and that error can grow exponentially as you're making some rollout.
Yeah, and I guess the rollout will also depend on the policy in a way.
The rollouts, well, I guess if you do multi-colored tree search, then you could try different actions, not the actions that are only chosen by the policy. You can just say, well, I just want to try different actions.
Okay, thank you.
Yeah.
Does anyone else have any final questions? Okay, if not, I think we'll end here because we're a bit after 1 o'clock already. So thank you very much for the presentation today, Yi, and thank you, Rich, for introducing him. And next week we are having someone from BioWare come in. So next week's presentation is co-hosted with Tech Alberta. So we'll hopefully have the more details about that one soon. They'll be posted on the AI seminar, and we'll also be sending it out to the mailing list. So you should be receiving an email about that. And if not, have a wonderful weekend, everybody, and we will see you next week.